Before we look at the actual contract, let's look at another helper function that I defined in this utils module, and I called it getCredentials. It takes a Plutus address, and if we look at the definition of a Plutus address, then we see that it is a record type with two fields, one address credential, which is the payment credential, and one address staking credential, which is the optional staking credential. So now what are these credentials? Let's see. So for credential, there are two cases. One is a pub key credential, which is given by a pub key hash, and the other one is a script credential, which is given by a validator hash. So these are the two cases of addresses, the ones that existed before Alonso, just corresponding to pub keys, and now with the dawn of Plutus, also those where spending is controlled by a validator. And the staking credential, there are also two cases. So it can be a credential, so again a pub key hash or a validator script, or it can be a pointer. So there are these indirect staking credentials that point to a specific position on the blockchain. And this helper function getCredentials is supposed to try to extract the public key hashes contained in an address. So the result will be nothing if it's a script address, and if it's not a script address, if it's a pub key address, then it will be a just with the corresponding payment pub key hash and optionally a staking pub key hash. So this is just a simple exercise in pattern matching. So if it's a script credential, the first part, then we immediately return nothing. If it's a pub key credential, then we have this component, and then we look at the staking part, and if that's not there, then we just return nothing here. If it's a pointer, then the overall result will be nothing again. And if it's staking hash, then again two cases. If it's a script, again the overall result will be nothing. And if it's pub key, then we return the corresponding stake pub key hash. So if any script is involved anywhere, or if such a pointer is involved, then we return nothing, and otherwise we give the pub key hash and optionally the stake hash. And I'm also using this function later for these two derived helper functions, basically just projection. So given an address, I try to extract the pub key hash, or I try to extract the stake hash. So I'm just using this function and then look whether the corresponding pieces are there or not, and then return the payment pub key hash or the stake pub key hash accordingly. So with this preparation, we can now look at this module token.offchain, where I define the minting of tokens in the contract monad. So first I define a type for the parameters, and this is very similar to what we also used in the CLI. So I need the token name of the token to be minted, I need the amount that's supposed to be minted, and I need an address. This is now not the change address, it's the address where the tokens are supposed to be sent after the minting. And I do that because now I'll be dealing with HD wallets, so where there are many, infinitely many actually, addresses belong to a wallet, and I want to specify which one I want to use. Or of course it could also be external. I could send the newly minted tokens to somebody else. So I just want to have control and specify that explicitly, because I don't have a control over the change address, that just gets picked by the wallet. But I want to specify exactly where the freshly minted tokens go. This is a helper function. We can look at that in a second, but let's look at the main function. So it takes these token parameters, and it's a contract, an expression in the contract monad. And it will return the currency symbol. We don't really need this now, but when I wrote this code, I still thought about maybe implementing the Oracle example. And for the Oracle example, you have to do something with the token you mint, and you in particular have to know the currency symbol. So I wanted to return this from this monadic expression, but we don't need that for now. Okay, so I don't need to write any state, and I also don't have any endpoints, so I can leave these polymorphic, and error messages I just use text. Okay, I log that I'm starting. Then I look up the address where I'm supposed to send the minted token to. Then I use the helper function that I just showed you. And if that returns nothing, that means there is a script somewhere contained in this address. Then I just stop with an error. And if it's not nothing, so I do have a payment pubkey hash, and I have an optional staking pubkey hash. Then I use some function that we haven't looked at yet. It's called get unspent output, and it does what it says. So it looks for an unspent output in the wallet that is basically running this contract. So I get a reference to this output. Then there's another function provided by the library called txOutFromRef. So given such a reference, it gives me the actual output. That could also fail, so it actually results in a maybe, but I know that the output is there because I just got this oref from this get unspent output. So I can be sure that there is an actual output there. So using from data.maybe and f mapping that over this contract, I get the actual output. So recall, contract is a monad, so it's in particular a functor. So from just goes from maybe A to A. So f mapping this from just into the contract monad now goes from contract maybe output to contract output. And this symbol here is just another way to write fmap. So I'm logging some information that I found this unspent output. I'm also looking up its value. So this output has a field CITXOut value. So I look up the value to log that. So now a couple of helper definitions. So I look up the token name from my parameters. I look up the amount. Now I compute the currency symbol. This comes from the on-chain part we looked at in the beginning. So there I had a function token policy to get the policy, and also a function token cur symbol to get the currency symbol. And I now have this oref that I need as the first parameter, and the token name and the amount. So now I can compute the value that I want to mint. So recall in the CLI we pieced that together in the shell script. But here, of course, it's much higher level, so I can use the value singleton function, which takes the currency symbol that I now have, the token name and the amount, and then creates a value consisting of that. Now I want to have a constraint that says I want to pay this value to the given address. And this is now a bit unfortunate, and that's the reason why I had to give this get credential function, because there are, for the two cases, whether staking information is present or not, there are two different constraints in the libraries. So one is called must pay to pubkey, and it just takes a payment pubkey, and it will pay to the address where the staking information is nothing, it's not there. But if you want staking information, then you need a different constraint that's called must pay to pubkey address, and that takes the two pubkey hashes, the one for the payment and the one for the staking information. So I have, depending on whether I do have staking information in my address or not, I must use these two different constraints. And therefore I needed this get credential helper function to actually extract the X and the Y from the given address. So in both cases, provided it's not a script address or scripts are not involved there, but that case we already excluded here right in the beginning. In both cases, I basically get the constraint that I want to pay value, val, to the given address. It's just a bit more complicated because I have to do this case distinction. For lookups, I must specify the minting policy. So for that I can use my token policy function from the on-chain part that I showed you earlier, that we also used to actually serialize the policy and write it to disk, and then in particular compute the policy ID from it. And I must specify, as before, the unspent outputs. So I only need the one, so I can use map singleton, so creating a map with just one key and one value, and use the ORF and the O as value. And then I can define my constraints. So the last one here is the C, which I computed here, which says I want to pay the value to the provided address. Then I have a constraint to do the minting. So I want to mint this value. And I have a constraint that I need to spend this OREF. That's important because the minting policy will check that this given OREF is actually spent by the transaction. Recall that's the trick to use to make sure that there can only be exactly one minting transaction for this currency symbol. Okay, now I want to submit this. Earlier I used the library function submit tx constraints with for this, but now I defined this helper function, and the reason is I wanted some more extensive logging, and I also have to take care of this min ADA. If you look here at in the C constraint, I just say I want to pay this value, this newly minted value, to the given address. But as we also saw in the CLI, that wouldn't work because I need to add this min ADA value. And I could of course do that by hand here, but I can also use something called adjust unbalanced transaction. So that gets an unbalanced transaction, which I can make with function make tx constraints, which takes lookups and constraints. So this results in unbalanced transaction. And then there is this function adjust unbalanced transaction, which will add the min ADA to all the outputs. So now I still have an unbalanced transaction, but at least it fulfills this min ADA requirement. Then I just lock this unbalanced transaction. Now I can balance it. So there is a balance tx function, and I call the result unsigned because now it's balanced but unsigned. I lock this. And finally there's something called submit balance tx, which takes a balanced unsigned transaction, signs it, and submits it. So that result I call signed, and I lock that and return it. So we could do all of these steps except for the adjust unbalanced transaction one with what we used in the previous weeks. But I just wanted to split it into these steps, balancing, signing, and submitting, because I wanted to log all the intermediate results. Because when I first tried it, there was a problem and it didn't work, so I wanted as much information as possible. And I also have a version here that's without lookups. So that's similar to the built-in functions that we have used before. There were two versions, one with lookups, one without. So I just use that. But I think I don't even need it. I'm not sure. At some point I thought I would later need this. Okay, and that's it. So I just use this to actually adjust and balance and sign and submit my transaction, log information, and return. So in particular, note that this contract only submits this one transaction and then stops. So it's not running for long. It, in particular, is not blocking on endpoints. It doesn't wait for input from the user. It simply does its thing and then stops. I also wrote a simple emulator trace to test this. So it's in module week 6 trace. And it uses this simple version, run emulator trace IO. So I don't need to specify any specific initial condition. And all I do is I take the first mock wallet and then I activate my contract. For this wallet 1 mint token, I need to specify the W and the S parameters. Remember I said I could leave them polymorphic, I don't care. But in order to use it here in the emulator trace monad, I must specify two specific types. So I choose unit for the writer monad part because I'm not writing any information, and I use empty for the schema. so there are no endpoints. And as parameters, I just make up a token name, so USDT in this case, an amount 100,000, and as address I use wallet 1's address. So these mock wallets, they only have one address. So there's different to, for example, dataless wallets where you have these infinite addresses. And that's it. I can try this in the REPL test token. And I see that indeed I end up with one wallet that now has 100,000 USDTs. I wrote a second contract because I think it's better to explain the PAB if there's not just a single contract. And in particular, if there's not just a single contract that does have neither endpoints nor return any information nor run for a prolonged time. So as I said, the mint token contract that I wrote doesn't return any information to the user, it doesn't have endpoints, and it returns immediately. It submits the transaction, the minting transaction, and then stops. And that is not the typical behavior of contracts in the PAB. So to show more features, I wanted to have a different contract as well that behaves differently in this regard. It also doesn't have endpoints, so I don't have an example of a contract with endpoints because I personally feel that endpoints are not really that useful most of the time. But nevertheless, at least it's a long-running contract that will provide some information to the user, so I can demonstrate how to get that out of the PAB later. So the idea is it's a contract that monitors an address. So it takes an address as argument, as its only argument, and then it will query the blockchain and report the value sitting at that address. And it will do that forever. So how do I report this value? Well, I use the W parameter. And as I said before, that must be a monoid because the idea is that it starts with mempty, and then each time I tell a value, it gets appended to the current value. And in this case, I'm choosing the monoid last value. So what is this last? That comes from data.monoid. We can try it in the REPL. So if I ask for information last, we see it's simply a new type wrapper around maybe A. And the justification for it is that it changes the monoid instance of maybe A. And the idea is, as the name suggests, it always keeps the last just. So if I start, mempty, let's say I use, I don't know, characters. So the mempty is last nothing. So, but now if I have, let's say, last just A and append last just B, I now have the B. But if I now do a last nothing, it's still the B. So it remembers the last just, as I said. So if there never has been a just, it will be nothing, and as soon as there has been a just, it will remember that. So in our case, I want to, like in regular intervals, write the value I find at that address, and that means it will forget what used to be there before, and the state, the observable state, will always be the last value I found at that address. So that's a quite common choice, at least in simple examples for this monoid. I don't have endpoints, hence I can use empty for the schema here. So I just log a message in the beginning, and then I call this go, which will call itself recursively, so this runs forever. And in each iteration of this, I use UTXOs at for the given address to find all UTXOs at that address. And now I fold over these UTXOs. Remember, I want to find the value contained at that address, so I must add the values of all the UTXOs. And how do I do that? Well, I fold left over the UTXOs. I start with the empty value, 0, and given the accumulator, the sum I have so far, and a new UTXO, a new output, I just add the existing value to the value contained in this output using again this underscore CITX out value that I also used in the mint token for one of the log messages. So now V contains the sum of all the UTXO values at that address, and I simply tell that. I tell just V. Then I wait for one slot and I recurse. So every slot this will update the observable state contained in this value.